Okay, welcome back everybody. We're going to start off our afternoon session here with Rick Chartrand talking about non-convex splitting algorithms and video decomposition. Thanks.
Okay. Right, thank you, and I'm grateful to the organizers for the opportunity to speak here today. So I'm going to start with a very brief example just to justify the value of looking at non-convex optimization. Then we'll look at some detail at a particular splitting algorithm in the convex case, and then look to see how we might generalize that to the non-convex case. Then we'll look at some examples featuring the example of video decomposition. Okay, so by now this is a fairly old example where we try to reconstruct a test image from some samples of its Fourier transform. And we want to exploit the fact that the gradient of this image is sparse. So we put a gradient into some kind of sparsity promoting objective function and minimize that subject to a data constraint that says that our Fourier transform should be correct on our sampling set. Now, if our F is the L1 norm, we know that promotes sparsity very well, and that can give us an exact reconstruction of this test image, provided we sample the Fourier domain. If we're sampling radially in this way, we need at least 18 lines. Now, if we cut the amount of data in half to just 9 lines, now if we use our L1 norm, we get a pretty poor reconstruction. But if we use a non-convex objective function instead, we're once again able to get a perfect reconstruction. And later in the talk, I'll be able to tell you just what non-convex F we use there. Okay, so we're going to look at a particular splitting algorithm, and we're going to do it in the context of this optimization problem. This is something that you could use for denoising if A were the identity, deblurring if A were a convolution kernel, or compressive sensing if A is some kind of measurement matrix with fewer rows than columns. And for me, everything is discrete, so my nabla here would be some discretization of a gradient operator. And now, we're going to look at a particular splitting that was introduced, at least in the image processing context, in this paper here. And we introduce a new variable, W, as well as a new term to our optimization problem. So you can think of W as being like a proxy for the gradient of X. And then this second term, you can think of as a relaxation of the equality constraint that would say W equals the gradient of X. So a fairly simple modification, but it turns out to do something quite powerful. Because now we've decoupled the operators in this functional, namely the gradient and A, from the non-smooth objective function, the L1 norm, because those are now acting on completely different variables. Non-smooth objective on W, the operators on X. And so we've decoupled the sort of hard parts, you could say, of this optimization problem and reduced this to two very simple subproblems. So this is a form of Douglas-Rackford splitting. The connection was made in this paper here, and gives us a very nice algorithm for solving this kind of problem. So if we look at this in a little more detail, well, if we just we've got two variables now to solve for, so we proceed by alternate minimization. We fix one variable, solve for the other, then alternate that, and iterate. It doesn't matter much what order you do that in, but if I write it this way, then this inner minimization over W is going to be some function of X, and then we can ask ourselves, what function is that? And that would basically be telling us what is our objective function as a function of X alone. And in this particular case, it's not too hard to calculate, and it has a name. It's the Moreau envelope of the L1 norm. And we can calculate that out, and it's basically a component-wise Huber function. So if we think about X as being an image, then at each pixel, the gradient of X would be some vector. And that vector is going to have a traditional kind of Huber function applied to it. So a Huber function splices together a quadratic near the origin with just an absolute value away from the origin with an offset to make sure that this function ends up being C1. So this is a very familiar function. It's been used in a lot of different algorithms, and now we can express it in terms of this Moreau envelope. So when you think of the objective function overall as a function of x as being this pixel-wise Huber function. Now, one of the valuable things about this is we have a very easy way of computing the solution for w for fixed x. First of all, it's a separable optimization problem, so we can compute the solution at every pixel independently. So you should interpret these operations pixel-wise, and at each pixel, you just take your gradient vector, separate out its direction vector, then take your magnitude and shrink it. So that's something very simple to do computationally, and the separability means this is also trivially parallelizable. So this is a fairly simple operation known as shrinkage or soft thresholding. Then if we fix fix w and solve for x, we would have a quadratic optimization problem to solve, which reduces then to a linear equation to solve, namely this one. And there are a lot of useful cases where we can solve this equation directly in the Fourier domain. For example, for my discrete gradient operator, if I use periodic boundary conditions, then this Laplacian will be diagonalized by the Fourier transform. And then if A is like the identity, as in denoising, or if it's a convolution kernel, like in deblurring, or if it is a sampling matrix of the Fourier transform, like in our introductory example, then A star A will also be diagonalized by the Fourier transform. So in any of those cases, we can solve this equation just by taking the FFT of the right-hand side, then divide by a fixed kernel, one that we can pre-compute because it doesn't change during the algorithm, and then take the inverse FFT. So that makes this algorithm very fast. And so, being such a nice algorithm, we would like to generalize this to the non-convex case, where everything works better. And there's really a couple of ways we can do that in terms of generalizing what we're doing to a non-convex objective function. And I would say the one that's probably the most natural to consider would be just taking this L1 norm and replacing it with something non-convex, such as an LP norm where p is less than 1. So then this is how our optimization problem would look. And this approach works, and it's been done. But there are some drawbacks to this approach. The biggest one, from my perspective, is solving for w is no longer going to be a shrinkage operator. And not only that, you can only write down what the solution for w is for a few special values of p. For example, if p is a half, solving for w would amount to solving a cubic equation. Not that that's hard, but it's not as computationally efficient as a shrinkage. But for other values of p, you have to proceed numerically. You don't have a way of analytically expressing the solution for w. And so what I prefer to do instead is generalize the Huber function instead. So now I take my quadratic and splice it with a pth power function. And again, with the offset and scaling, this will be a C1 function. And I've displayed here how that looks for different values of p. And in particular now, you can do this for any real value of p. If p is 0, you just want to interpret this in a weak sense and basically get the logarithm of absolute value t. For negative values of p, what you get is this new objective function is bounded above. And if you compare this with the L0 objective function, which is constant away from 0, that's a nice property to have. And in fact, in many cases, I get my best results using negative values of p. Okay, so now in the L1 case, our Huber function arose as a Moreau envelope of the L1 norm. So if I'm going to start with my sort of p Huber function, I need to ask myself, is there some function that this is the Moreau envelope of? It's certainly not immediately obvious. But now if we write down the relationship, this would say that h is the Moreau envelope of g. We can re-express that just by picking apart this quadratic term in terms of the Legendre-Fenchel transform, also known as the convex conjugate. So we get something, a fairly familiar operation going on. And now we're going to use this to define G just by moving the conjugation operation to the other side. And then we're going to take advantage of the fact that by construction, this function of t here is convex for this p Huber function. As a result, if I now use this relationship to define my G, then if I take the convex conjugate of both sides, then the double conjugate on the right will cancel out, and that will reduce down to the relationship that I want to be true. So that establishes that there is this function G that I can define in terms of the Legendre-Fenchel transform, whose Moreau envelope will be the Huber function, the p Huber function. So we're applying some convex analysis, even though our H and G are non-convex. So this is how the function G looks for those same values of p. Away from the origin, it's very similar. It looks just like the pth power function. But now near the origin, instead of being quadratic on some interval, it's going to have a cusp. And the subdifferential of that cusp, in other words, the slopes of the external tangents, is just going to be the same interval that the Huber function was quadratic on. So you get kind of a nice duality going on there. But now the trick is I can no longer write down analytically what this function G is, except for, again, these special values of p. If p were a half, then I could write this function down in terms of solutions of a cubic equation. But I don't care whether I can write that function down. For my algorithm, I only care whether I can solve for w. And now things have been constructed so that solving for w is once again a form of shrinkage. But it's now sort of an LP analog of shrinkage, where we have this spatial dependence, you might say, in terms of the amount that we shrink. And since for me, p minus 1 would typically be a negative exponent, this means if the gradient is small, we actually shrink more strongly. So it tends to promote sparsity even more strongly than the regular soft thresholding. Then just the other thing I should say about the algorithm, we like to have a convergence that w should equal the gradient of x. We also might want to enforce an equality constraint. And so to do that, we can use a type of augmented Lagrangian method known as the method of multipliers, or in the particular context of this kind of splitting, referred to as split Bregman on this paper here, where we introduce these, you could either call them Bregman variables or Lagrange multipliers, which we then update at every iteration. Interesting thing is in a lot of cases, these kind of step sizes could just be 1 and not have to change throughout the iteration. But that's all I'll say about this in the interest of time, and because I think other speakers will be touching on these kinds of topics. So let's now look at some examples of what this algorithm approach can do. So Stan asked if you get uniqueness. Yeah. So in other non-convex examples, like just straight LP minimization, minimizing the LP norm, then you can prove uniqueness under the same kinds of hypotheses that you would need to get uniqueness of the L1 norm, which is typically, L1 norm with an equality constraint is not strictly convex. So it's similar, but for this particular algorithm, I don't have a uniqueness established. Okay, so let's just come back to our introductory example. Now I can tell you what that objective function was. It was the p Huber function with p being negative a half. And it's the negative exponent really is necessary to be able to reconstruct this phantom from so few data. The algorithm is also very fast. So these are 256 squared images. And just running in MATLAB on my laptop, this takes 21 seconds. If I add a 10th line of samples, increase the data just a little bit, the running time goes down to 5 seconds. So a very fast algorithm. And that's not even exploiting the natural parallelism that's possible with this algorithm. Okay, now let's look at a more recent family of examples. Decomposing high-dimensional data It's also a form of geometric modeling of high-dimensional data.
And when you use these negative p, do you start with that negative p from the start, or do you first do
Like a continuation?
p and then a continuation?
No, so Ingrid is asking, do I just start with a negative p or I do a continuation? I've often get asked, does it help to start with p equals 1 and then march the p down? No, I actually start with a negative value of p right off the bat. And it doesn't get stuck in the local minimum, even though you think it should. So I'm not going to get into this talk, but generally these non-convex methods, as long as you do them in the right way, they don't get stuck in local minima, even though there's a bajillion of local minima to worry about. Okay, so this would be a form of geometric modeling of high-dimensional data. The nicest example to think of is video, where now every frame of your video would correspond to one column of this matrix D. Then we're going to separate it into a low-rank component plus a sparse component. And then the low-rank component represents a low-dimensional model of our data, much in the way you'd get in principal component analysis. But things change a lot by having this sparse component, because now you have a model that is more robust to outliers, and not just outlying points of the data set. You can now have the freedom to sort of jiggle individual coordinates of every point. So you have a much greater flexibility in terms of how you're robust even. Because we're not penalizing the size of the discrepancies at all, we're only penalizing how many there are. So that lets our low-dimensional model L better describe the bulk of our data set, while these discrepancies in the data set can also contain useful information. So this has been referred to as robust PCA, which is actually an older idea, but for example in this paper here, people are now leveraging the recent technology in terms of sparse optimization to this robust PCA problem, and with very nice results. But now the usual problem is we'd like to solve this optimization problem, but we can't because it's NP hard. So the usual thing to do is to look at a convex relaxation, but the usual thing for me to do is to look at a non-convex relaxation. And so now what we take our sort of our proximal analog of the LP norm, so to speak, and apply it to our vector of singular values of L. So if P were 1, this would be the nuclear norm that we saw in earlier talks. And then apply that same proximal P norm to the entries of the sparse matrix S. Then we have our data fidelity term, the Frobenius norm. It's just your usual Euclidean norm in the matrix space, so to speak. And we use our method of multipliers to get an equality constraint at convergence. So this is the approach that was used in this paper here in the convex case. So I'm applying it now in the non-convex case. And I still call this tractable. I don't have any theory supporting this, but in practice, local minima just don't seem to be an issue with this. So let's look at an example. So this is a traffic clip from North Hollywood, just outside Universal Studios. We have some cars stopped at a traffic light. Whoops. Oh dear. Oh no, it went back. Okay. See, is this Adobe Reader? Okay. So on my computer, this just plays. That's the usual game for multimedia demonstrations. Works on my computer, not on this one. So, okay, so for each column of this matrix has 76,800 rows. And we have 288 columns with a video clip of about 12 seconds. And so we have some cars stopped at a stoplight. We've got a bunch of cars parked in the parking lot that are stationary. And, forgot my, I'm sorry? I'm sorry, I can't hear you. Oh, that if I take it out of full screen, it might work? Worth a try. Oh, thank you. If this computer has a reader. Not my day. Okay, so let's see how much time I'm wasting. But okay, so this is the matrix D that we decompose into a sparse component and a low rank component. And see, when you work in the government, you learn to kind of be stubborn. Not give in to obstacles. Oh, and that just fell out, didn't it? Wait, this better be a good example, eh? Okay. Okay, so we see cars stopped at the stoplight, then they start going again. We see a bicyclist going down the sidewalk. A car went by in the parking lot. We have a bunch of stationary cars and so forth. Okay, so a lot going on in this scene. Now we look at the video corresponding to the sparse component S. Basically what it's going to give us is motion. So you see the cars that are moving, then when the light turns green, the moving cars appear. There's the bicyclist. There's a pedestrian who was actually pretty hard to see in the original video. So just by removing the background, we're able to kind of better hone in on kind of the interesting information, you could say. Then you look at the low rank component, and it's basically everything stationary. When the light turns green, these cars disappear. And notice the traffic lines get driven over in the original video, but here they get filled in automatically. This is, well, it's LP with P being negative a half. It's of just S, that sparse component, not the gradient. Well, that's coming. Okay, so now what if our video is noisy? So now we certainly won't want to have an equality constraint, so we take out the multiplier. But now we want to penalize something like the total variation of S. We want to put a penalty on the gradient, as Stan was suggesting. And now I'm going to put an exponent on my total variation that, once again, is going to be less than 1. So now here's the splitting algorithm that I apply to this. There's now more splitting going on in the noiseless case. So V is now a proxy for S. W is a proxy for the gradient of S. And I can still solve for L, V, and W using shrinkage. Of course, with L, that has to be wrapped in with the SVD, or at least a partial SVD. And my problem in solving for S is still quadratic. And as long as I use my periodic boundary conditions, I can still solve this with 2 FFTs. So it still ends up being a very efficient algorithm. Okay, so why am I bothering with an exponent on my total variation that's less than 1? Well, total variation, the thing about images, it penalizes the length of edges. So it's not going to preserve shapes as well. Or in 3D, it's the surface area boundaries. So if we want to preserve more complex shapes, then we can put an exponent q in there. And now, instead of penalizing length for images, we're penalizing a 2 minus q dimensional measure instead. Or in 3D, a 3 minus q dimensional measure. So this doesn't penalize shapes as much. And just a quick example in the image context. So with the smaller the value of Q, the more complex the shape I can preserve. So these long, thin fingers, they get washed out by TV, or the sharp corners, they get rounded off by TV. So here's our noisy video clip, and it's actually even noisier than it looks like on the screen, because we see a lot of compression artifacts. I think those look like DCT artifacts. Then these sparse component, not perfectly denoised, but pretty good. We're still going to maintain the distinction between moving and stationary, still see the bicyclist and the pedestrian, and much of that noise has been removed. And whereas the low rank component is actually pretty much perfect, this tells me that algebraic regularization is stronger than analytic regularization. And then finally, I'll show you the residual. And again, this will actually look a little worse because of the correlation in the noise, but there is some signal in the noise there. And then I'm not showing you the Q equals 1 version, but that's the distinction in this case, is that there'd be a little bit more signal in the residual, in the convex case. And if you think about L plus S as being like a denoised copy of the video, I get better fidelity with Q equals 1/2 versus Q equals 1. And I've overused my time, so I'll stop right there. Thank you.
Thank you. We have time for a question.
Use different values of Q for, you did a non-convex for both the, normally do is the, the nuclear norm part, and for the one norm, instead of using the one norm for the S, you use the same Q, right?
So certainly, I'm actually using 3 things at this point now. One in the gradient, one in the sparse component, one in the low rank component. Right. In principle, in terms of the algorithm, those all 3 could be different. Yeah, I set it up so that I was doing L and S, so I was using the same, it was set up to be the same one, and the gradients to be different, and I just happened to settle on the same value for all 3. But they could have, all 3 could have been different. I've certainly tried Q equals 1, even with the other P being non-convex.
And the second question is, you have no convergence, even for the earlier version without the noise, because there is this issue of non-uniqueness, of multiple solutions. Do you have proofs of any?
Yeah, so I have nothing. I believe that sort of Yima's group and so forth, I believe in at least one of their papers they do have proof of convergence. Oh yeah, no, when P is less than 1, yeah, I have nothing. Yeah.
But for P, less than 1.
That's right, yeah.
We have time for maybe one quick one while Mario sits.
Okay.
Guillermo? Well, Mario sits.
Okay, one of these you can.
But you have another question.
So you talked a lot about robust norms, but then you did the low rank plus bars plus L2. Why not to do low rank plus a robust norm? Because that's basically what the sparsity is doing. It's just taking care of outliers. So you put a robust norm in the feeding term, and you can take care of outliers. So there is no explicit need when you go to the environment you're working with non-convex norms, to put that explicit outlier there, unless you want something particular of that outlier. I wonder why not just put a robust feeding there.
Okay, so yeah, Guillermo was, I guess, basically asking, why am I using the Frobenius norm to penalize the error when instead of using something more robust? There'd be more robust outliers.
And then get rid of the sparsity terms that you did that.
Yeah, so.
Because you're working with a lot of non-convex, so you're
Right. Right. So yeah, I guess so. I agree that that can be done, and actually, in the imaging context, we're just starting to look at that. At that particular juncture, it was convenient algorithmically to have the quadratic term, because then you get a shrinkage. But there is actually a way around that that I hope to feature in a future talk.